Last class I discussed about the exciton dissociation. Exciton can transport in the organic semiconductor through the Foster mechanism and through the Dexter mechanism. Right? After transportation of the exciton, exciton has to dissociate it at the interface or at any kind of the organic semiconductor. Inside the organic semiconductor or at the interface of the organic semiconductor, right? So, for dissociation, how acetone can dissociate at the organism, at the interface of the organic semiconductor or inside the organic semiconductor, right? Normally, in case of the organic semiconductor, this device, right? Organic devices, okay, acetone dissociation, okay. So, suppose exciton means this is a bounded electron hole pair. This is called as a exciton, right? So, in case of the organic semiconductor, Frankel exciton is produced. Okay. So, this Frankel exciton, there is one Bohr radius, or this Frankel exciton is the electron that is strongly bounded with each other. Okay, we have to apply the high electric field to dissociate. Okay, to break this exciton, right? So the one is a Bohr radius. This exciton has a Bohr radius of 1 nanometer. Okay, with a high exciton binding energy. That is 50 milli electron volt. Is that is the exciton binding energy. So to break this exciton, we have to apply the 50 volt external power supply, or we have to apply the 50 volt internal voltage. So we cannot apply, or we cannot produce such amount of the 50 volt voltage inside the organic semiconductor to break this Frankel exciton, right? So this is feasible. This is not feasible. Okay, so how can you dissociate this Frankel exciton? Okay, so if you create a one energetic barrier, if you produce a internal electric field, high amount of internal electric field inside the organic semiconductor, so then we can dissociate the exciton. Okay, so this is a one organic semiconductor, this is a one energy level. So along with this, if we create another organic semiconductor layer, okay, so this is one LOMO, one HOMO 1, LOMO 2, and the HOMO 2, right? So for that, suppose in this material, this is one material, OS organic semiconductor 1, this is organic semiconductor 2. Okay, one electron hole pair, this is created. Okay, so this is first, this has to transport through this organic semiconductor layer. So when it will get some electric field, that time it will dissociate it. Okay, for that it has to transport, it has to find any kind of the electric field. So when it transport towards the interface, at that interface it can see the some energetic barrier. Okay, that is suppose delta LOMO. Okay, delta LOMO, that is equal to LOMO 1 minus LOMO 2. Okay, so this delta LOMO helps the exciton to dissociate. Okay, so when the electron hole pair that is produced inside the organic semiconductor layer. Okay, so at that moment it will transport through the at the interface. Okay, so it can dissociate into free carrier by releasing that delta LOMO energy, right? So in other case, suppose electron hole pair that is produced, okay, in this organic semiconductor 2 layer. Okay, in this case, this electron hole pair will transport towards the interface, right? At this interface, it will release the delta HOMO energy to create the free hole. Okay, So by releasing delta LOMO energy, the electron hole pair can create the free hole, okay, when it is created at the organic semiconductor 1. If the acetone is created at the organic semiconductor 2, by releasing delta HOMO energy, it can produce the free hole, okay. So that means in case of the organic semiconductor device, the electron transport towards the LOMO level and hole transport towards the HOMO level, okay. In this way, acetone can dissociate into free carrier. So we can also create the multiple interfaces, right? So this is the one interface we can create by employing two different semiconductor layers, right? This is about the acetone dissociation. So main is that is the LOMO 1, okay. The LOMO 1, that should be less than LOMO 2 or HOMO 1. That should be less than HOMO 2. Suppose it is a 3 electron volt, right? It should be 3.5 electron volt. Suppose it is 5 electron volt, it should be 5.5 electron volt. Another point is, this is the one point. Another point is that delta LUMO, that should be greater than acetone binding energy. Also delta HOMO, that should be also greater than acetone binding energy, okay. So that means, so whatever binding energy is there inside the acetone, so we have to apply the more energy to dissociate the electron, right? These are the main criteria to dissociate the electron hole pair in organic semiconductor, because the Frankel acetone is created, okay. Now coming to the next mechanism, that is the electronic transport. Okay, so electron can transport through the organic semiconductor based devices by injection of the electron from the outside of the device, or by dissociation of the acetone. But after dissociation of the acetone, free carriers can produce inside the organic semiconductor layer. Okay, so based on the different application, the different mechanism we can use. So when the acetone is dissociated into the free carrier, that will be used for photodetector application, and for organic light emitting diode application, injection mechanism is required, okay. So electron can transport inside the organic devices by two processes, okay. One is the by injection mechanism, second is the by dissociation. In this case, by dissociation, first the acetone will produce, so from the acetone we will get the free carrier, okay. That is used for organic photodetector application. By injection mechanism, first we will create the free carrier inside the device, okay. Once you create the free carriers inside the device, that will produce the acetone to illuminate the light, okay. That is used for organic light emitting diode. In both cases, we will get the free electron and hole inside the organic semiconductor. So how electron and hole will transport, or how electron will inject inside the device, and how electron will and hole will transport after the dissociation at the interface. So this I will discuss now, okay. So first I will discuss about the injection mechanism. Okay, injection mechanism. So to transport the electron inside the organic devices, injection mechanism plays an important role, okay. So how it is related with the device, okay. So there is a metal semiconductor interface, okay. So in case of the metal, what function is there, okay. Metal and the suppose semiconductor, this is the semiconductor, suppose organic semiconductor, this is the metal, okay. The interface between metal and organic semiconductor, that plays a crucial role for injection mechanism. How the electron can inject from metal to semiconductor, or how the electron can transfer from semiconductor to metal. Okay, this interface plays a crucial role. Okay, so two different mechanisms are there. Okay, one is the thermionic emission, first one. Second one is the tunneling mechanism. Tunneling mechanism. Okay, in some cases two mechanisms are valid in a one system. Okay, what is the tunneling mechanism? Suppose at the interface, this is the metal and organism got the interface. Now we can see here I am drawing first one. This is the metal. Suppose this is the so suppose this is the interface. Okay, you can see some band bending is there at the interface. This is the metal, this is the semiconductor OS one. Now in this case you can see the energetic barrier this is delta E, that is very less. Okay, the energetic barrier is less at the interface between metal and organic semiconductor. Due to the less energetic barrier, the electron can easily transport. For thermic emission, what is the condition? There is less energetic barrier between metal and organic semiconductor. Okay, and if some interlayer is there, the interlayer is the very thick. This is the thick layer. This is organic semiconductor is also very thick layer. Okay, this is thick layer and very thick layer, and the energetic barrier is very less. So electron can easily overcome this energy. Okay, to transfer from metal to organic semiconductor or organic semiconductor to metal. Both way it can possible. Okay, so when the electron injection is there, so flow of the electron inside the semiconductor, then flow of the current. Okay, the thermionic emission current. When the tunneling phenomena will occur, suppose metal, this barrier. So this and E delta E, this is very high. Okay, is the metal organic semiconductor, and this is very thin layer and high barrier. And another point, the thermal emission, this is applicable for high temperature. So now sometimes you can see the device structure will also change according to the temperature. This is applicable for high temperature. Okay, at low temperature sometimes you can see the some change in the energy level, or in a normal temperature also. So if you see, if the one thin interlayer is there, its organism layer is also very thin, right? This is the metal layer. Okay, metal layer, and this is the very thin organism layer. And there is a large barrier gap at the metal and the organic semiconductor. So electron flow cannot overcome this barrier. Okay, but electron can tunnel from this side to this side. Okay, that is called the tunneling mechanism. Okay, or the current flow due to the tunneling mechanism is called the tunneling current. These two mechanisms are there. Okay, in these two ways the electron can transport through the organic semiconductor. Okay, now the injection current. So when the electron will flow by following these two processes, so then they will get the injection current. Okay, so the injection current, sometimes if we calculate the injection current, this injection current, that is depending on the two mechanism. There is a thermionic assisted tunneling mechanism. Okay, so this entire process are related with the injection current. Okay, now the injection current. Now I want to discuss the two processes. Okay, suppose the injection current, that is also depending on the work function of the metal. Okay, the work function of, because I told that the energetic barrier between metal and organic semiconductor, due to this energetic barrier we will get the sometimes thermic emission current or tunneling current. Okay, Now the first case I want to discuss. Suppose in case of the first, uh, the work function. Okay, this is the organic semiconductor layer. Now this is the function of the cathode or metal. Okay, this work function is large. Okay, this is the LOMO level. HOMO. So what will happen? So normally what will happen at the interface? Okay, at the interface we will get the interfacial dipole. Okay, the interfacial dipole that will play the dominant role in case of the injection mechanism. Okay, due to the interfacial dipole that is creating the energetic barrier at the metal and organic semiconductor interface. Okay, the interfacial dipole that is creating the energetic barrier. Okay, now so above this level, HOMO level, there is a vacuum level. Okay, there is a vacuum level. Now I am choosing one metal which work function is very much larger than the LOMO level. Okay, suppose this is 2.5 electron volt and this is almost 5 electron volt. Okay, now what will happen? So here the one interfacial dipole will create which can create the energetic barrier. Due to this, so one vacuum level is there, right? One vacuum level is there. Okay, you can see that will move upward direction. Okay, that will move upward direction. Here we will get the interfacial dipole. Okay, here we will get the interfacial dipole. Why I am getting the interfacial dipole? Due to the large energetic barrier between the metal and the organism. For this case, I will get the interfacial dipole. The shape of the interfacial dipole that is in the upward direction. Okay. Now, so due to first I am choosing the high work function material. Okay. So for that we will get the high energetic barrier and interfacial dipole. Okay. The band bending that is in the upward direction due to the high energetic barrier. Okay. So then the electron requires a high amount of energy to overcome this barrier. Okay, so it is not possible. Okay, flow of the hole can possible. Hole can move from this HOMO to this metal. Okay, due to the low energetic barrier, but electron cannot move. Okay, okay, due to this mechanism. Okay, the electron is not moving from the metal to organic semiconductor, such kind of the energetic barrier or interfacial dipole is created. Okay, this is the one mechanism. So in this case we will not get any electron or the current due to the electron. If we are getting electron, okay, so less amount of efficiency I am getting. So efficiency that is decreasing with increasing the work function of the cathode. Okay, next is the second case. In case of the second one, the opposite one. Okay, the metal work function is energetic barrier between metal and the organic semiconductor. Metal means cathode. Okay, that is very less. So due to this energetic barrier, due to the such condition, okay, due to this such condition, the vacuum level shift towards the downward direction. Okay, vacuum level shift towards the downward direction because it is moved in the upward direction. Okay, due to this the at the interface we will get a such amount of interfacial dipole. Okay, to here high due to the high energetic barrier, such kind of the interfacial dipole I am getting. The high amount of energy is required. Okay, to overcome this barrier. Okay, here in this case, due to the less energetic gap, such amount of the interfacial dipole you will get, less energetic, because the interfacial dipole that is creating the energetic gap. Okay, why these two things are happening due to the flow of the electron. As the electron can flow, electron can overcome this barrier. Okay, in this case electron can easily overcome this barrier, so such amount of the dipole is creating. So the vacuum level is shift towards the downward direction due to the flow of electron from metal to organic semiconductor. Why the electron is flowing? Because less energetic gap between the metal and the organic semiconductor. So then flow of electron is possible in this case. Why? There is a less, and suppose it is 4.1 electron volt, it is 4 electron volt. Okay, so in this case we can see such kind of the interfacial dipole and the shift in the vacuum level and this kind of the energetic barrier. Here the flow of electron is possible, but flow of hole is not possible in this case. Okay, these two are the main mechanism. In this case we will get the high high efficiency, injection efficiency. This is the injection efficiency in this case, when there is a less energetic gap between cathode and the organic semiconductor. Okay, the efficiency is decreasing with increasing the cathode work function. Right, this is about the injection mechanism. Okay, now interfacial dipole, that can also create at the organic interface. This is a one organic semiconductor, this is a another organic semiconductor. Okay, so organic semiconductor, which mechanism is for dominating in this at the organic semiconductor? Dissociation mechanism. Okay, dissociation mechanism. Okay, so due to the energetic gap between organic semiconductor 1 and organic semiconductor 1, here also we will get interfacial dipole. Okay, so interfacial dipole, so that means the structure of the interfacial dipole, it is moving in the upward direction or it is moving in the downward direction. The structure of the interfacial dipole, that can influence the dissociation mechanism or injection mechanism. The same interfacial dipole can create at the organic interface. Now, how can you manipulate the interfacial dipole? By adding different kind of the structure, by doping different kind of the material, we can manipulate the interfacial dipole, structure of the interfacial dipole. Whether we should control the flow of electron inside the device, or we should increase the flow of the electron inside the device. So this we can manipulate by implementing different kind of the structures. So this is about the injection mechanism or interfacial dipole, or how the interface will change at the organic interface. So next class I will discuss about the same kind of the electronic transport mechanism, the bulk electronic transport, the hopping mechanism. Thank you.